Okay, 2.1 worksheet. You believe you have the ability to read your opponent when playing rock, paper, scissors in order to anticipate what they're going to throw, and you would like to know if that's true. You spend a week playing against anyone who is willing. In a total of 80 games, you win 35 of them. What is that as a percentage? 43.7. Okay. What is the probability of winning a game of rock, paper, scissors? If you just randomly guess, what's the probability of winning? And it looks complicated, right? Because you have to think about what you play versus what they play, but it actually doesn't come down to that. Rock will either win, lose, or tie, right? So it's a 33% chance of winning. So in every game, there is a 33% chance of winning. So if you can anticipate what the other person does, you should be able to get better than 33%. Right? Okay, so we need a histogram, and we're not going to actually draw the histogram. So how could we take a dice and simulate a 1/3 probability? We just count 2 of the sides. So I've chosen 1 and 2. So I have here 60 boxes. You need to roll the dice 60 times. Every time you get a 1 or a 2, you circle the W. And every time you don't get a 1 or a 2, then you circle the L. Okay? So I'll pause the video, give you guys some time to roll those. Once you roll them, so answer questions 3 through 6. Question 7 doesn't really make sense yet. All right, welcome back. So number 3, what does each roll represent? One game of rock, paper, scissors. Everybody agree? Okay. So what does rolling a 1 or a 2 represent? Winning a game of rock, paper, scissors. Do we know if it was a rock or a paper or a scissors? No. The only thing we're measuring is win or lose. Okay. We don't have any data about which one you chose and whether that one won or not. We just know if it's a win or a lose. So what does a 3, 4, 5, or 6 represent?
Not winning.
That'd be losing the game. Okay? So we can turn a lot of situations into a dice roll or a coin flip or drawing a name out of a hat. Okay? And using that, we can come up with some data about what we would expect to happen. So we would expect 33% wins. So how many of you got less than 33%? Just one. How many of you got more than 33%? Some of you didn't raise your hand. Okay. So the number 7, so your answer, what percentage of your rolls represented a win? And then get rid of the word histogram, that shouldn't be there. So does your answer for number 6 support your claim that you are better than average? And remember we got, was it 43.7? 0.8? Okay. So this is our rock, paper, scissors number from the first paragraph. Right? Okay. And then your answer for number 6, most of you were bigger than 33%. Some of you were below 33%. Did anybody get exactly 33%? How many were there? 60? You could get 20, right? So in this case you could. If it was 50, then you wouldn't be able to, but 60 you could. Okay. So, can you use this number to decide if that number is correct? Or is, sorry, let me say that again. Can we use our answer for number 6 to determine if you are better than average? No. So is one round of, what was it, 60? Is one round of 60 enough information to give us a sense of what's going to happen? So even if this is 25%, right? 25% does not give us enough information to decide if that is high enough, right? So if you got, let's say, 38%, would you think you're better than average? Well, you are technically above the average, but there's going to be some randomness in there, right? So you have to be far enough from the average that we are more certain that you are above average. Okay? So we need to do this dice roll game a lot of times, right? And you just rolled the dice 60 times and you're already sick of it. So we're not going to roll a dice anymore. Okay? So on your Chromebook, I want you to do a Google search for Rossmann One Chance. So search up Rossmann One Chance. And we're going to use this website all the time. Okay? And that's not the page you see, right? Let me do the Google search and then look. Okay, so if you go to this, Rossmann Chance Applet Collection, on the right side, you want to select one proportion inference, and then you get this. Okay. So, in that second paragraph, in the probability of heads box, write 0.3333. So we are counting a coin, we're flipping a coin, and we want to say the probability of flipping a coin and winning is 0.3333. How many rolls are going to be in one simulation? 60. So we're going to type in 60 here. Okay. Now, click Draw Samples. And then we have I have 22 successes and 38 failures, and it puts a dot right here at 26 on mine. Yours is going to be something different. So we just simulated 60 rolls of a dice using one click of a button. So now draw, I don't know, a couple dozen samples and watch your histogram. So just keep clicking Draw Samples. What? So I'm at 32 samples, I'm going to stop. Okay, look at number 8. What does each dot in the histogram represent? So the number of, in this case heads, but what are we simulating? So the number of rock, paper, scissors wins in a 60 round, in a 60 game round. So each dot is the number of wins in rock, paper, scissors in 60 games, a round of 60 games. Okay, now look back up here. Do I have a nice looking histogram? Not yet. How many times do I need to push this button until I have a nice histogram? And the answer is, you can never do too many, but 1,000 is usually enough. So I'm just going to go up here and change my number of samples to 1,000, and then draw samples one time. And now I have a pretty good looking histogram. It's still not perfect. So we're going to do this over and over and over and over. 1,000-ish is usually good enough. If you don't have a very good looking histogram, then do more. So I could draw samples again, draw samples again. And the more I draw, the better my histogram looks. Okay? So number 9, what is the shape of this histogram? Normal. Okay, number 10. We have this option over here that allows us to choose the statistics. I can either choose the number of wins, or I can choose the proportion of wins. Which one makes more sense? So if I do number, I'm going to say the number of wins is, oh, I don't know, 18, 19, 20, 21. But we are trying to get this 33%. So almost always we are going to use the proportion of successes. Okay, looking at your histogram or my histogram, doesn't matter. What would you guess the average to be? So this bar is the height. It looks to be about point, so that's 1, 2, 3, 4, 5. So each one of those is 2. It looks to be about 34, somewhere in there. 33, 34. Okay, is anybody confused yet? What about the standard deviation? So the standard deviation is a little bit harder. So I draw this normal curve, and I find that inflection point, and I find the distance from the average to that inflection point, which is about 1, 2, 3, 4 bars, and each bar is 0.2. So my average is about 34%, and my standard deviation is about 10%. Oh, wait, was it 4 or 5? 1, 2, 3, 4, 7. Sorry, 8. So it's about 8%. Okay? What does that mean? What does 8% mean? Okay. If you are truly guessing when playing rock, paper, scissors, 68% of the time, your percentage of winning in 60 games is going to be 33% plus or minus 8%. Okay? All right, now, we have a computer here. We don't actually have to guess what the average and standard deviation are. We could just click this button that says, tell me the summary statistics, and it spits out an average and an SD, and I was off by a little bit, but yes. Okay. So, what does the average of the histogram tell us in this case? Interpret 33.4%. What does 33.4% mean in this situation?
The rock, paper, scissors game.
And good, I'm glad you said all. Can we actually take all the rock, paper, scissors games? can we ever get to the population? No. So we could say in the long run, or after many games, after many rounds. So after many rounds, and what was a round again? 60 games. So after many rounds of 60 games, your win percentage should be about 33.4% if you are guessing, right? So I need to add if you are guessing. What if you're not guessing? It should be better than that, right? Okay. Does everybody understand 14? Okay. 15. What does the standard deviation of the histogram tell us in this case? Any idea? So what was it? 6.1% tell us? If you understand this, you're on your way to understanding statistics. Okay, what would the range, so we need to add a number to that.
4 plus or minus 6.6.
So we could say this in several ways. About 68% of all 60 game rounds. Now what?
Will be within plus or minus 1 standard deviation of the average.
Right, and we're actually going to use the numbers because we have them. So we want to be very, very specific in stats. About 68% of all 60 game rounds should fall between 33.4% plus or minus 6.1%. Okay. Does everybody get that? Now, most of the time we don't use 68% because that's only 2/3. So most of the time we use 95%. Okay? So you could also say, and this is an equivalent statement, I could cross this off and say 95%, but then I would have to change this
Plus or minus
12.2%. Right? And that's what we consider pretty normal. Not normal like a normal curve, but that's what is expected. You can draw the line anywhere you want, but we usually draw the line somewhere around 95%. Or really what we do is we calculate the probability of being wrong, and we say we are willing to be wrong about 5% of the time. Okay? So if we use that as the rule, 16, does this histogram support your claim that you are better than average at rock, paper, scissors? What was your score? 43.5%. And
That's within 2 standard deviations.
so 33.4 plus or minus 12.2, that's going to give us 21.2 up to 45.6. Okay, what does that range tell us? If you land in that range after 60 games, That was expected. That is just as good as rolling a dice. So, does this number support the claim that you can read your opponent? No, it does not. Okay? And no is never enough in stats. You have to say no. 43.5% is well within the 2 standard deviation range. Now, congratulations, you have just learned statistics. That's all it is. So, in statistics, we come up with a situation that we want to study, okay? We set up a model based off of flipping a coin or rolling a dice or some other number that somebody gives us, and then you go out and you play rock, paper, scissors. And we compare your results to the coin flip, and we use that information to say you did better than the coin flip, or you did worse than the coin flip, or you did the same as the coin flip, and that is statistics. And we're just going to be doing the same thing over and over and over in all sorts of different situations. There will be new formulas and all that, but if you get this, that is statistics. That's all we're going to do, just in different ways. Okay? Now, you might look at this and say, hey, I did better than average. And that's true, you did. But you only did it once, right? If you consistently get 40-something% every time you play a 60-round game, then if you do that enough times, then you will be able to claim that you are better than average. But if you only play one 60-round game and you land in this window, that is not enough information to say that you're better than average. True, your score was higher than the average score. But when rolling dice, it is totally normal to land anywhere in that window. Anything outside that window we would consider to be abnormal. Right? So the next time you do it, you might end up with 28%, and then 31%, and then 35%. But if you consistently score more than 33% every time you do a 60-round game, that would be evidence that you're better than average. But a single 60-round game has to land outside this window to be considered better than average. Okay? All right, turn the page. A friend claims to have ESP, which is extrasensory perception, which is the sixth sense, and it can mean lots of different things. But in this case, it means if she gives you a deck of cards and asks you to shuffle it well, and then she guesses the color of the top card, and then you flip it over to verify it, and she is right 57 out of 80 times. Is that enough to support her claim that she has ESP? Okay? So what percentage of games did she win? 57 over 80 is 71.25%. What is the probability of winning by simply guessing? 50%. So it's 26 out of 52, right? We're excluding the jokers. So half the cards are red, half the cards are black. So the probability of winning is 50%. Okay? So we go into our app. I'm going to do this from my desk. What should we select as the probability of heads? 0.5. And our sample size?
52. Or wait, no, 80.
Good. So it's not the number of cards in the deck. It is how many times she played the game. She played it 80 times. And how many simulations do we want to do? 1,000-ish. So I draw 1,000 samples. and I have my normal curve, okay? Okay, sample size was 80. What does each dot in this histogram represent?
One round of 80.
1 round of 80 guesses. So every single dot in that histogram is 1 round of 80 guesses. Okay, 23. Does it make more sense to use the number of successes or the probability of successes? Probability. We want to stick with probability. Okay. So write down the average of the histogram, which in this case is 49.7%. So I ended up with 49.7%. And the standard deviation is 5.5%. Okay, what does the average mean?
After playing a large number of games, you should expect your answer to be, like, your probability
Right.
to be around.
So after playing many, many rounds of 80 games, 80 guesses each, the average should be around 49.7%. Okay. What does the standard deviation mean? And we're going to use the 2 standard deviation rule. You could use the 1, and it's true, but we're going to use the 2. So the standard deviation tells us about 95% of what?
Of rounds.
80 guesses. About 95% of 80 guesses should be within I guess we should say, should be correct. Should be correct within what?
Within plus or minus
49.7 plus or minus.
Should be within 49.7 plus or minus 2 times 5.5. Does anybody not get that calculation? So you have to understand that. If you don't get it, don't let me move on. Everybody good? Okay, so what is that? So that's 11, so 38, oh, that's a 4. 38.7 to 60.7. So, if you play a single round of 80 guesses, you have a 95% chance of landing in this window. Okay? And what did she guess? 71.25%. Which means we think she must have ESP. Okay? All right, at the start of class tomorrow, I will let you do the remaining questions. Have a good day.